Hello everyone, welcome back you all in this new video where we are going to design sloped or trapezoidal foundation by manual approach. This complete problem we are going to solve in 5 important steps. In the first step we will see the problem statement along with the brief general discussion about the sloped or trapezoidal foundation design. In the second step, we will see how to decide in-plan dimension of the footing as length, width and depth. In the third step, we will see design for the reinforcement along the length and width of the footing. In the fourth step, there will be design checks against the one-way and two-way shear. And in the last step, we will see the final design schedule and detail of this footing. First of all, try to understand the problem statement. We have to design a footing for a rectangular column of size 300 by 600 which is carrying a service load of 1666.67 kilonewton. The safe bearing capacity of the soil at the proposed land is 200 kilonewton per meter square. The material that we have to use for the design of this foundation will be M25 as a grade of concrete and Fe415 as a grade of steel or rebar. Now let's start the design. In the first step, we need to find out the in-plan dimension of the footing. So try to understand what does mean by the in-plan dimension of the footing. So requirement of this length and requirement of this width is what in-plan dimension of the footing. So how much the length, how much the width of the footing should be for the safe design is mainly depends on the two important factors. That is, first one is what? How much the load needed to transfer to the subsoil coming from the column. Whatever the load coming from the column, that actually we need to transfer to the subsoil. So you need to know this, how much load is coming from the column. Second important factor you need to know, that is what? How much the bearing capacity of the soil on the proposed land. How much the bearing capacity of the soil is there. If you are going to take the ratio of this load divided by SBC of the soil, it will tell you about how much area of the footing is required. And the same thing we are going to execute in our example. With all of this given data, let's start the solution. So we have given the service load of 1666.67 kilonewton. But in this service load, we have to add the self weight of the foundation also. And we are considering the self weight of the foundation as 10% of the load that is coming from your column. So you may ask a question, why we are going to add this self weight of the foundation in the service load? So in actual, only the column load is not going to be transferred to your subsoil. This is 1666.67 kilonewton. It is coming from your column, and this column load is not only going to be transferred to your subsoil over which your foundation is rested. There is an addition of your self weight of the foundation also. This column load is going to be transferred plus self weight of the foundation is also going to be transferred to the subsoil. But to calculate the self weight of the foundation, it is important to know that what is the length of the footing, what is the width of the footing. These two dimensions, including of what is the depth of the foundation, with these three dimensions only you will be able to find out the self weight of the foundation. But without of having these three dimensions as length and width and depth of the foundation, you will not able to calculate the self weight of the foundation. That's why what we are going to do, we are going to consider the 10% of service load. Whatever the service load coming from your column, we are going to consider the 10% of that. So that is going to become 166.67 kilonewton. If you are going to add these two values, so you are getting the total load that is going to be transferred to your soil will equal to 1666.67 plus 166.667. It is going to become 1833.34 kilonewton. If you want to calculate the area of the footing, that is going to become area of footing equal to this much the load which is going to be transferred divided by SBC of the soil. If you are going to take the ratio of these two, you will get the value of area of the footing required as 9.1667 meter square. Now, in respect of area of the footing required, we have to find out the length and width of the foundation. But there is a note for deciding the length and width of the foundation. So we have to decide the length and width of the footing such that the pressure distribution at the base of your foundation should be uniform. And to ensure the uniform pressure distribution at the base of footing, the projection X on all sides of your foundation from the face of your column up to the edge of the foundation, it should be what? Same in all the direction. This X and this X, this X and this X, in all direction these values should be same. Then only you can ensure that the pressure that is going to be developed at the base of your foundation from your soil mass will be uniform. And this you can ensure only when your column is going to be positioned centrally over your foundation slab. if the CG of your column and if the CG of your footing is going to be coincide, then only we can ensure that your foundation is going to be subjected with the uniform pressure distribution. And if you are ensuring that uniform distribution is there of your pressure, so we can say that the settlement will also be uniform. But in a situation when you are not succeeded to maintain the uniform pressure distribution at the base of your foundation, then what will be there? There will be an unequal settlement in your foundation or in your subsoil. That's why this projection in all directions should be what? Same. So here length of the footing and width of the footing is equal to 9.1667. Area of the footing is there. I am going to call it as what? The equation first. Now here length of the footing I am going to consider along this direction, longer span. It is I am going to call it as length of the footing. So length of the footing is going to become x plus x, that is going to become 2x plus side of your column along this direction, dimension of your column. So that is going to become a plus 2x. Likewise along the width I am going to consider it as bf. Width of the footing is equal to width of your column plus 2x. So it is going to become length of the footing and width of the footing. I am going to put these two values in the equation first. When you are going to put these two values in the equation first, along with the dimensions of your column as 600 and 300, you will get this equation finally. And if you are going to solve this equation, you will get the quadratic equation. And after solving of this quadratic equation, you are getting the x value as equal to 1.29 meter. Put this value of the projection in this length of the footing and in this width of the footing. So you are getting the final length requirement. Length of the footing requirement is what? 3.18 meter. And along the width of the footing, the size of the footing is required as 2.88. But in actual, we are providing slightly more than that of the required value. So instead of 3.18, I am going to provide here as 3.2 meter. And for the width, the demand is what? 2.88. So slightly more than of this value I have to provide, that is going to become 2.9 meter. If you are going to multiply these two dimensions, so you will get the final area that we are going to provide as 9.28 meter square. This is what the total area we have provided. Now against this application of the loading, how much the intensity of the upward soil pressure is there, we need to find. See, the column load, the load coming from the column plus self weight of the foundation is going to be transferred to your subsoil. Soil is going to impose the reactive force, that we are going to call it as what? Upward soil pressure. So we need to find out this upward soil pressure. So upward soil pressure will equal to the total intensity of the loading which is going to be transferred to your soil. That is what? 1666.67 divided by 9.28, total area of the footing provided. After that we are getting what? Upward soil pressure as 179.59 kilonewton per meter square. If you are going to design sloped foundation or trapezoidal foundation, you have to decide two important things. That is what? The first, how much the projection is there from the face of your column up to this edge. Okay, so this projection I am going to consider as 75 mm, and this projection will be along all sides of your column from its face. Second, how much the depth of the foundation is there at its edge. So at the edge I am going to say that the depth of the foundation is 230 mm. This D2 is equal to 230 mm. So these two things you have to decide first.
Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall. And at the end of this training program, we will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next.
Now, after knowing the length of the footing and width of the foundation, we need to find out the how much the depth of the foundation is required. So for the flexural criteria, we need to find out the how much depth of the footing is required. But before of that, we need to calculate the movement along the length of the footing, movement along the width of the footing. So how to do the calculation for the movement along the length, along the width? Try to understand that first. So here we have to calculate the movement at the face of your column along the length of your foundation, as well as you have to do the calculation for the movement at the face of your column along the width of your foundation. In both of the direction you have to calculate the movement at the face of your column. So here I am going to explain how you can do the calculation of the movement at the face of your column along the length of the footing. What is the formula? So the formula is going to become upward soil pressure. How much the upward soil pressure is there? This is what your upward soil pressure. So upward soil pressure value multiplied by width of the footing. Okay, if you are going to do the calculation along the length of the footing, if you are going to find out the movement along the length of the footing, so this width you have to consider, width of the foundation, multiplied by this projected part beyond the face of your column. This projected part, this projected span you have to calculate. So that is going to become what? That will be your L, and square of that divided by 2. So this projected part, how you can calculate this projected part? So the formula is what? Total length of the footing. What is the formula? Try to understand. Total length of the footing minus a side of your column, or dimension of your column along the considered direction, along the length of the footing, that will be your A, divided by 2. So you are getting this cantilever portion, this projected part. If you are going to put this value in your formula, upward soil pressure multiplied by width of your footing multiplied by, if you are going to put this value, suppose if you are getting it as x, so put this value x square divided by 2. So you will get the movement along the length of the footing. And same concept you have to apply for the width direction, along the width of the footing. Okay, so just come back to our example. Here movement along the length of the foundation, it is going to become upward soil pressure multiplied by 2.9 is the width of the footing multiplied by projected part. Projected part is how much? 1.3 meter. How I have calculated this value? That is what? Total span of your footing is what? Along the length 3.2 meter. Side of your column is what? 0.6 meter, and divided by 2. If you are going to calculate it, you will get the 1.3 meter. Put all the values and do the calculation. You will get the movement along the length of the foundation as 440.11 kilonewton meter. We have to apply the factor over this as 1.5. You will get the ultimate movement along the length of the foundation as 660.15 kilonewton meter. Same you have to do for the width direction along the width of the footing, upward soil pressure. But at this time, very interesting it is, if you are going to do the calculation along the width of the footing, if you are going to calculate the movement along the width of the footing, so length you have to consider. So it is the upward soil pressure, then length 3.2 meter multiplied by 1.3 meter square divided by 2, and you will get the value as 485.61 kilonewton meter. Here ultimate movement along the width is going to become 728.42 kilonewton meter. So this is what finally we are getting the ultimate movement along the length, ultimate movement along the width. So with these two movements, you have to decide how much the depth of the footing is required along the both direction. After knowing the movement along the length and width of the foundation, we have to find out the how much that effective depth is required. And for finding out the effective depth required, we need to use this formula. D required will equal to square root of ultimate movement in the considered direction divided by 0.138 FCK and the considered width. Now here is the question to decide how much the width we have to use. So as we know that we have calculated the movement along the length of the foundation at the face of your column, as well as we have calculated the movement along the width of your foundation at the face of your column. Okay, so in both of the direction we have calculated the movement at the face of your column. So here important is to know that how much the width of the footing in each direction is present along the length, along the width at the face of your column. So at the face of your column, along the length, if we are going to do the calculation, so this much width we have to consider only. and how much this width is, that is what 75 plus 75 plus this b width of your column. So column width is what 300. So that is going to become what total width available at the top of the footing at the face of your column is 300 plus 75 plus 75, that is going to become 450. So if you are going to do the calculation along the length, so this width you have to consider. Remember, when you are going to do the calculation along the width, this you have to consider. Okay, so first we are going to do the calculation along the length. So this width I have to consider. So depth required along the length of the footing, it is going to become, first we need to find out the resisting width at the top of footing. B equal to 300, this 300 plus this 75, it is going to become 450. Put all these values in this equation. So we need to know the ultimate moment along the length of the foundation. How much is that? So that is, let me show you. Here it is 660.15 kilonewton meter. So that I am going to put here as 660.15 into 10 raised to 6 divided by 0.138 multiplied by FCK, characteristic strength of concrete is 25, multiplied by width as 450. If you are going to put these values here, so you are getting the effective depth required along the length of the foundation as 652.07 mm. So keep in mind this much depth of the footing required along the length. Same calculation you have to do for along the width. Okay, so along the width, resisting width at the top of footing. So along the width we are going to do the calculation. So we need to consider this span. Okay, so this is what 75 plus 75 and this side of your column, that is what 600. So that I am going to put here as resisting width at the top of the footing as it is going to become 600, 75 plus 75. Overall it is going to become 750 mm. That all values I am going to put here as moment consider along the width. So along the width, how much movement is there? Along the width at this time, ultimate movement is 728.42 kilonewton meter. That I have given here 728.42 into 10 raised to 6 divided by 0.138 multiplied by FCK 25. Width available as 750. So we are getting the effective depth as 530.58 mm. Now two values we are having. One is the depth required at 652, another depth required as 530. So amongst these two value, we have to consider the maximum one, you know very well. So accordingly, we are going to do that. Consider the depth requirement as maximum of above two value. So I am going to decide that I will provide the 652.07 mm. So this is the effective depth. This is what actually the effective depth required for your flexure. Flexure means what? Resisting the deformation, resisting the movement. So for that 652.07 mm is required. But we know that your depth is not only going to be influenced by your flexural requirement. Only flexural requirement is not responsible to decide effective depth or overall depth. Another factor is there, that is what? Shear design. Shear design is also having the equal importance to decide the depth. And for most of the cases, your depth of the footing were influenced by the shear criteria. Shear criteria is one-way shear and punching shear, or we can say two-way shear. So if I am going to take this final depth for the later design, so there may possibly that my depth is going to be fail in shear. That's why for the safety concern, here I am going to directly consider that overall depth as 950 mm. So you may ask a question that then if you have to consider your depth directly as 950 mm, so why you have done this calculation for the flexure? That you may raise your query. So reason is what? Just to get the idea how much the depth of the footing we should select. For that we are going to first perform the flexural depth requirement. We are going to see how much the flexural depth requirement is. For that we are going to do this calculation. So overall depth here I am going to decide as 950 mm. So it is the overall depth. Now my intention to find out the how much effective depth is required. And you know that for finding out the effective depth, we should decide that how much the clear cover will be. So clear cover I am going to consider as 50 and diameter of bar I am going to consider as 16. So effective depth available will become 950 minus 50 minus 8 mm, half of your diameter of bar. So that you will get directly the value as 892 mm effective depth available in both of the direction. After knowing the effective depth, now I want to calculate how much the reinforcement required along the length of the foundation and how much the reinforcement required along the width of the foundation. In both of the direction, I want to calculate the reinforcement requirement. And the formula for calculating the reinforcement requirement is what? ST equal to 0.5 FCK divided by FY inside bracket 1 minus square root of 1 minus 4.6 ultimate moment in the considered direction. So we want to calculate the reinforcement along the length. So accordingly, the moment along that particular direction we have to consider. Thereafter, FCK multiplied by width that we have calculated earlier multiplied by effective depth available. This overall value you have to multiply with width available multiplied by effective depth. Put all of this value in this equation. FCK is 25, grade of steel is Fe415 and moment along the length, how much the moment is there along the length? So along the length moment is what? Ultimate moment 660.15 kilonewton meter. Don't forget that. So here I am going to put that divide by 25. This width, how much width is available at the top? So the width here we have calculated as 450 along the length. Okay, so here it is what? 450, 892 mm is your effective depth available. Square of that you have to consider. After calculating all these values, we are getting what? Reinforcement required along the length of the footing is 2262.52 mm square. This is I am going to call it as design requirement. But we have to cross check it with the requirement of the minimum reinforcement. So as per IS 456-2000, the code is saying that the minimum reinforcement in your concrete slab or foundation slab should be 0.12% of your width and overall depth. That value I am going to put here as 0.12% multiplied by overall width you have to consider. Overall width at the base. So along the length, if you are going to do the calculation, along the length, so width will be what? This overall width we have to consider as 2900 multiplied by 950. So you are getting what? Minimum requirement as 306 mm square. So you have to compare this requirement and you have to compare this requirement. And amongst these two requirements, you have to consider the maximum one. So among these two requirements, I am getting what? The maximum value as 3306 mm square. So we will provide this reinforcement. So for this reinforcement, I just want to know how much the spacing of the reinforcement I have to provide. So what is the formula for calculating the spacing of the reinforcement? Try to understand. Suppose this is your footing and we have calculated the reinforcement requirement along the length of the foundation, but this reinforcement is going to be distributed over the width. So spacing required over the width. Unit area of 16 mm dia is what? 201.06 divided by total area required along the length 3306 mm square multiplied by it is going to be distributed over the total width of your foundation, that is 2900. Length is what? 3200 mm and your width is what? 2900 mm. So your reinforcement is going to be distributed over the width. So that is going to put here 2900. So I am getting 176.368 mm. This much maximum spacing you can provide between the reinforcement that is running along the length and distributed over the width. So for that, you are allowed to provide the maximum spacing 176.368 mm. But for the safety concern, you have to lower this value by the roundup factor of 25 mm. So you can take 175 lower value. You can take 150 also, or you can take 125 also. So if you are taking as 175, that is also no problem. Okay. If you are taking 150, that is also okay, no problem. If you are taking 125, that is also no problem. If you are taking 100, that is also no problem. It is okay. But lower than of 100 value, that is not practically good or okay. So it is better to provide the spacing more than of what? 100 only. So here, what I can consider 175. But instead of considering 175, here I am going to consider 125 mm finally reinforcement spacing. So you may ask a question, our design is going to be satisfied with 175 mm. Why you are going to provide very small value of the spacing? Because why you are going to put the more reinforcement? So why it is? Because the presence of percentage of reinforcement will be good if it is in more percentage in the one-way shear check. Because the presence of percentage of reinforcement will take a part of resisting the one-way shear. So that's why I am trying to provide little bit more reinforcement. If you are taking 175, that will also be okay, no problem. but there may possibility that your one-way shear may get failed. Why it is? Because your one-way shear check, it is going to be influenced by two factors. One is your presence of percentage of reinforcement, and second one, depth available. So if depth is slightly less and if you are providing little bit more percentage of reinforcement, so one-way shear criteria will pass. If percentage is little bit less and you are providing more depth, your criteria will pass. So both are important to pass the criteria of one-way shear check. That's why what I'm going to do, I'm going to consider a little bit more percentage of reinforcement. That's only the reason of considering the more reinforcement or reducing the spacing. Now, finally, how much area of reinforcement is provided along the length? Area of steel provided is equal to unit area divided by final spacing 125 multiplied by considered total width. We are getting 4664.59 mm square area of reinforcement finally provided along the length, and this was 3306 mm square. This was the requirement. So we have provided the reinforcement more than of a required value. So we are on safe side. Same all calculation you have to do for your width direction along the width of the foundation. So same equation is there for finding out the area of reinforcement is required, but only the change here will be what? Your movement. So you have to consider the movement along the width. So movement along the width is how much? Ultimate movement along the width is 728.42 kilonewton meter. That I am going to put here as along the width 728.42 into 10 raised to 6 divided by 25. Here one more change will be there, width considered. So width considered will become what? 750 into 892 mm square, and put all this value here. So you are getting the answer as 2406.62 mm square design requirement. You have to compare it with the minimum requirement. Minimum requirement is what? 3648. So in comparison of this design requirement and minimum requirement is more, as similar to that of the case of along the length. Okay, provide 60 mm dia, same unit area is 201, spacing required 201 divided by final area that you are decided to provide 3648 multiplied by total length. See, you are going to do the calculation along the width, and reinforcement will also be along the width, but its distribution will be along length. So length you have to consider 3200. So spacing you are getting 176 again, and again I am going to provide lower value, and you know very well what is the reason why I am considering very small spacing as 125 mm center to center. So provide 16 mm dia at a spacing of 125 mm center to center along the width of your footing. Thereafter what next will be, final area of steel provided is equal to 201.06 divided by final spacing decided 125, overall span along the length. So 3200, we are getting the finally area provided along the width as 5142.14 mm square. It is not meter, it is mm square. Okay, so this is what the approach for calculating the reinforcement required along the length of the foundation, along the width of the foundation. Now, for the decided depth of the foundation, we have to perform the checks against the shear. And there are two types of these shear checks. One is your one-way shear check, another one is your punching shear check, or we are calling it as what? Two-way shear check. So, one-way shear check. For the performing of one-way shear check, we are going to follow the IS 456-2000 Annex B 5.1.1 clause. So, look at what this clause is saying about. So this clause is especially for the beams of varying depth, but this clause is also applicable for the foundation of varying depth. Here, as we are going to provide the trapezoidal footing or sloped footing, so depth is not fixed. Your depth of the foundation is going to be changed when we are moving towards the edge of the foundation. The depth of the foundation is going to be vary. So this clause of your IS 456 is applicable for finding out the nominal shear at your proposed section. Now the question is, at what section we have to perform the one-way shear check for the sloped footing. So for the sloped footing, as usual, we have to consider the critical section at a distance of D from the face of your column, and D is what? 892 mm from the face of your column. So go back to your figure and look at this. I am going to consider the critical section for the one-way shear check at a distance of D from the face of my column, that is what? D, and this is what? 892 mm. So when you come to this section, so the problem is what? Actually, if you are going to do the any checks at the face of your column, so we know that what is the overall depth of the foundation at this level, 950 mm. But when you come to this section, so there is very difficult to know how much the effective depth is available at this section. So for finding out the effective depth at this critical section, we need to go through some geometrical calculation, some mathematical equations we have to apply here to find out the how much effective depth is available at this critical section. So for that, it is important to know these dimensions. Okay, so from the face of your column up to the edge of footing, we know that 1300 mm is there, and we are going to consider the critical section at a distance of d from the face of your column. So it is what, 892. So if you are going to subtract 1300 minus 892, so you are getting the value of 408. This is the first thing. Second thing, if you want to calculate the distance from the face of this projection is what, 75 mm. So beyond this 75 mm, how much this projection is? So how much it will be? 1300 minus 75. So you will get this value 1225. So these all dimensions are very important to know. And here objective is what? We need to find out the how much this effective depth is at this proposed critical section at a distance of d from the face of your column for performing the one-way shear check. So I want to know this y dash, because I know that this height, it is what, 230 mm. Beyond of that only I have to calculate this y dash. So how you can calculate this y dash? Just come down and look at this. The depth at the edge of projection from the face of your column is what? 720 mm. At this edge depth we are having what? 720 mm. I want to calculate the depth at this level. Okay, y dash. So how you can calculate this y dash? So the formula for calculating the y dash will equal to 720 multiplied by this projected dimension beyond the critical section, that is what, 408. You have to take the multiplication of these two things divided by this projected portion for this 1225. If you are going to take this ratio, so you are getting the y dash value as 239.8. Now you have to add this value with the edge depth. Okay, so edge depth, we have calculated the depth as y dash here. So y dash, you got the value of 239.8. Then plus 230. So if you are going to add 230, so you will get total overall depth. But our intention is to find out the effective depth, d dash. So for finding out d dash, the formula is going to become what? 239.8 plus inside bracket 230 minus clear cover minus half of your diameter of bar. So you are getting the d dash value as 411.8 mm. Now b dash, how much the resisting width available at that proposed section for the one-way shear check at a distance of d from the face of your column. So the formula for that is what? Width of your column plus 2 times effective depth of your footing. So if you are going to do the calculation for this, we are getting the resisting width as 2084 mm. Now the shear force at that critical section is going to become what? 179.5, that is what, upward soil pressure multiplied by projection beyond the critical section. So this is what our critical section, and the projection is what? Projection is 408 mm. So it is going to become in meter 0.408 multiplied by full width. We are going to do the calculation of the one-way shear along the length. So we have to consider the width. So the width is what? Total width 2.9 meter. So it is what? The service load. I am going to multiply this service load with the 1.5 value. So we are getting the factored shear force at that critical section as 318.75 kilonewton. With all of this calculation, we have to use this equation for finding out the how much nominal shear is going to be developed at this critical section. So the formula for that is what given in your IS 456-2000. Nominal shear will equal to your shear force value plus m into tan beta divided by effective depth divided by width multiplied by effective depth. So you need to come back to your calculation, and here you have to see that same formula I am going to apply here. Now here, where tan beta will equal to 720, the height at that section, how much the height here, it is what? 720 divided by this span, this width. How much this width is? That I am having here as 1225, that you can see here. Now I am going to put the value here as, see, 720 divided by 1225. So we are getting the tan beta value as 0.587. Put all these values in this moment calculation. Next, we have to find out the ultimate moment at the critical section that we have considered for the one-way shear. So this is our critical section. At this section, I want to calculate the moment. So what is the formula for calculating the moment at this section? That is going to become upward soil pressure. So our upward soil pressure is what? 179.59 kilonewton multiplied by total width. Total width is what? If you are going to do the calculation along the length of the footing, so we have to consider the full width. So that is what? 2.9 multiplied by this projected part beyond the one-way shear check section. So the section beyond of this, how much? This is what? This much section is there. So this projected span I need to know. So that is what? 408 mm. It is going to become 0.408 meter. So that I am going to put here square divided by 2. This is what the service moment you are getting. If you are going to multiply this value with 1.5 factor, so you will get the ultimate moment, or you can say the factored moment at that particular section. Now we are having all the values as ultimate shear force. We are also having the ultimate moment. Effective depth we are also having at that proposed section. Effective width available at that proposed section. Everything is there. Tan beta value is also there. So we can calculate the nominal shear at that proposed section of one-way shear. So I am going to put all the values in this equation tau v. Now taking all the values in the equation of nominal shear, so we are getting the nominal shear value as 0.263 MPa. Now we have to compare this nominal shear with your critical shear value. And if you are getting your nominal shear less than of your critical shear, then we are going to say that our design is okay. But in a situation if you are getting the nominal shear more than of your critical shear, in that situation we need to revise your design. So for finding out your critical shear, we need to know the percentage of reinforcement available at your proposed section of one-way shear. If you are going to do the calculation along the length of the footing and you have considered the critical section at a distance of d from the face of your column, so we need to find out the percentage of reinforcement at this section. So for that we need to know the how much area of reinforcement available throughout the length of your footing. So just go back to calculation of the area of reinforcement and find out how much the area of reinforcement provided along the length of the footing. So along the length of the footing we have provided the total area of reinforcement as 4664.59. So that I am going to put here in the calculation as ST 4664.59 divided by width at that proposed section as 2084. At a one-way shear section, the effective width available as 2084, that I am going to put here as 2084 multiplied by overall depth of your foundation. So with all of this calculation, we are getting the percentage of reinforcement available at the one-way shear section as 0.24%. Now, in respect of available percentage of reinforcement and grade of concrete, as in our proposed example, there is a grade of concrete as M25. We need to find out the how much critical shear capacity is there. So for that we need to refer the IS 456-2000 table number 19. That will tell you how much the critical capacity of your section is. But here in our calculation the percentage of reinforcement is 0.24. When you go to look in table number 19, so there is no any option which is giving the 0.24 value. So your value is coming in between 0.15 and 0.24. So we need to do the interpolation between these two values. So for 0.15% for the N25 grade, the value of critical shear is 0.29. For 0.25%, the value is 0.36. And our percentage is what? 0.24 in between these two values. So we need to do the linear interpolation. And after completion of the linear interpolation, we are getting the value of critical shear as 0.353 MPa, Newton per mm square. Now compare nominal shear with your critical shear. So we are getting the your nominal shear value is less than of your critical shear, hence that it's safe in one-way shear. We don't need to revise the design. Your project percentage of reinforcement as well as depth of your footing is safe. Now we can proceed for the performing of two-way shear check. After satisfying the one-way shear check, we are going to do the check for the two-way shear, and we are going to refer the IS 456 2000 page number 58 clause number 31.6.3.1. So let's consider the critical section at a distance of d by 2 from the face of your column, and as we know that our effective depth is 892 mm. If you are going to take the half of this, so you will get the value as 446 mm from the face of your column. So we are going to consider the two-way shear area, two-way shear section all around the face of your column at a distance of d by 2 from the face of your column. So here I just want to calculate this perimeter length from all its sides. Okay, so how you can calculate this perimeter length? So that is going to become along the length, this is what d by 2 plus d by 2, it is going to become what, d plus side of your column in this considered direction as a. So d by 2 is going to become d plus this a, and why I am going to multiply this value by 2? Because this is the one side, this is the another side. Likewise, if you are going to do the calculation along this side, so d by 2 plus d by 2 is going to become d plus width of your column you have to put here as b multiplied by 2. Why it is 2? Because this side and this side, total 4 sides it is having. So after doing the calculation, we are getting the value of perimeter length as 5366 mm. What next I have to calculate? I have to calculate the shear force at this two-way shear section. So the formula for calculating the shear force as this two-way shear section is equal to upward soil pressure multiplied by total area of your footing as length of the footing multiplied by width of your footing. So length of footing multiplied by width of the footing will give you total area at its base minus the area of this critical section. So how you can calculate the area of this critical section? This length multiplied by this width. So simple formula is what? D by 2 plus D by 2, it is going to become D plus this 600 size of your column along this direction. So 600 plus D 892. If you are going to add these two value, so you will get 1.492 multiplied by this side. How you can calculate this side? Very simple. It is 300 plus this d by 2 plus d by 2 is going to become d 892. So that is going to become 1.192. So if you are going to do the calculation for this only, so you will get the service shear force. If you are going to multiply this value with 1.5, so you will get the factored shear force. So the factored shear force is going to become 2020.8 kilonewton. Thereafter, I want to calculate the effective depth at this section d by 2 from the face of your column. But I know the depth up to this level. So that is what, 230 mm. I only have to calculate this y dash. So how you can calculate this y dash? So I am going to do the calculation with this triangle. So here how much depth is 720. How much this projection is 554. How much this total projection is 1225 mm. So with all of this value, I am going to do the calculation for the y dash. That will be 720 multiplied by 854 divided by 1225. Then we are getting the value of y dash as 501.94 mm. Now you have to add this y dash value with this 230. But actually I want to calculate the effective depth. So my effective depth will be up to the center only. So adding of this 230 totally, it will be wrong. So you have to subtract this effective cover as 58. So that I did in my calculation. Let me show you. Just come here. Total y dash is 501 plus 230 minus 58. We are getting the effective depth at the proposed section of the two-way shear as 673.94 mm. Now I have to calculate the nominal shear at the two-way shear section. So that is what? Shear force, ultimate shear force divided by d dash multiplied by perimeter length. So d dash perimeter length and your shear force, you will get the nominal shear as 0.558 MPa, or it is in Newton per mm square. This value we are having. Now we have to compare this nominal shear force with your critical shear. We are going to use the IS 456 2000 page number 58. So come back to your IS 456. So the formula for calculating the punching shear is Ks into tau c, where Ks equal to 0.5 plus beta c, where beta c is what? Being the shorter side of your column to the longer side of your column. And this Ks value should be maximum up to 1 only. You are not allowed to consider the value greater than 1. So we are going to do the calculation in our problem. Here we are knowing that our side of column is what? 300 by shorter side divided by longer side as 600. So that is going to become 0.5. So I am going to put here as 0.5 plus 0.5. So it is going to become 1. K's value is totally going to become what? 1. And if K is equal to 1 means your critical shear value is equal to Ks into tau c. So if K is equal to 1, then critical shear is going to become your tau c. Then tau c equal to 0.25 square root of FCK, that I can show you in your code also. So your tau c is equal to 0.25 under root of FCK. So that we are going to do here. Our characteristic strength of the concrete is what? 25. And this 0.25, the value of the critical shear you are getting as 1.25 MPa. Now compare this nominal shear with your critical shear. So by comparing this nominal shear with your critical shear, we are getting the value of nominal shear less than of your critical shear. Hence that we are going to say that our provided depth is safe in two-way shear also. We don't need to revise the depth or we don't need to revise the design. At the end, we have to prepare the schedule and details for the final design results. So here first we are going to write about the size of the foundation. So total length of the footing we have provided as 3200 mm. Total width of the footing we have provided as 2900 mm. And overall depth of the foundation we have provided as 950 mm with a break of the depth of the foundation at its edge as 230 mm. And remaining depth is going to become 720 mm. So in this break you have to write the depth of the foundation. Thereafter, how much the reinforcement we have provided along the length of the footing, we have provided 16 mm die at a spacing of 125 mm center to center, and along the width of the footing we have provided 16 mm die at a spacing of 125 mm center to center. So this is about the schedule. Now how to prepare the detail of the design result? So this is about the sectional elevation, that is showing what? Detailing about the reinforcement for this sloped footing. So in both of the direction we have provided 16 mm dia at a spacing of 125 mm center to center, and in plan detailing of the reinforcement is what? Here the length of the footing is 3.2 meter, width of the footing is 2.9 meter, and the reinforcement along length 16 mm die at a spacing of 125 mm center to center, along the width 16 mm die at a spacing of 125 mm center to center. So this is what? Sectional elevation detailing, and this is the in plan detailing, and this is what? Complete schedule. So in this way you have to do the complete design of sloped or trapezoidal footing along with its scheduling and detailing.
Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall. And at the end of this training program, you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1000 participants have benefited from this training program. Now you are the next.